For this example, we're given a state of stress, state of plane stress, sigma x, sigma y, tau xy. We're given that this state of stress exists in a ductile material, which has a yield strength of 250 megapascals. We want to determine if the maximum shear stress theory will predict that the material will fail under this state of stress, and in comparison, will the maximum distortional energy theory predict failure of the material. We know that our first task here is to find sigma 1 and sigma 2, because it's within the sigma 1, sigma 2 plane where we make the decision as whether failure will occur. What's shown here on the right-hand side is the blue hexagonal region. If the state of stress falls within that, well, then we can say that the maximum shear stress theory says that it's safe. If the state of stress falls within the red ellipse, the maximum distortional energy boundary, then we say that that theory will say that the material is safe. So again, we need to find sigma 1 and sigma 2. That's going to be based on our calculations of sigma average and the parameter there of r. Sigma average then being the average value of sigma x and sigma y. So sigma x is 125. Sigma y is a minus 40. We get an average value there of 42.5 megapascals. The parameter of r, which is interpretation, is that's the radius of Moore's circle, sigma x minus sigma y divided by 2, plus tau xy squared. So the values that we are given here, we put in 125 minus a minus 40 divided by 2 squared plus 105 squared. That number ends up being 133.6 megapascals. From these two, we calculate the principal stresses. There are sigma 1 and sigma 2, sigma average plus r. That number gives us 176 megapascals. The other principal stress, which is sigma average minus r, that gives us minus 91.1 megapascals. So what we see is that sigma 1 and sigma 2 are of opposite signs. So in the sigma 1, sigma 2 plane, it's in the fourth quadrant. What I'm going to do is draw an expanded view of the fourth quadrant of the sigma 1, sigma 2 plane, so we can better see the difference between the two theories in terms of failure prediction. So again, I'm going to show here in blue the maximum shear stress theory. It's going to be this line here, which is minus sigma y here and sigma y there. And then the ellipse here is going to be maximum distortional energy. So again, this is the sigma 1 axis and sigma 2 is here. We want to know first, is that state of stress, sigma 1 and sigma 2, those principal stresses within the blue hexagonal shape? So the first thing I'm going to do is calculate what's called the load line. The load line is just a tool that we use to determine whether that state of stress is within the boundary or not. So the load line is the equation of sigma 1 is equal to some slope times sigma 2 is some slope m times sigma 1. Well, the slope here is equal to minus 42.5 divided by 133.6. So that slope is minus 0.517. So the equation of that load line is minus 0.517 sigma 1. So I'm going to call that equation 1. in order to find out how things stand relative to the maximum shear stress, I'm going to write down for the first part here our maximum shear stress boundary. And that's the blue line. So that's sigma 2 is equal to sigma 1 minus the yield strength there of sigma 1. So what we want to do is find out where the load line and the maximum shear stress boundary intersect. In other words, we're going to set equation 1 equal to equation 2. So this becomes 0.517 sigma 1 is equal to sigma 1 minus sigma y. So from this I get that sigma 1 is equal to sigma y divided by 1.517. The yield strength we know was given to us as 250 megapascals. 1.517, that number becomes 164 megapascals. And just to give this a better name, I'm going to call this sigma 1s. That's where the load line crosses the shear stress boundary. So this is the point I'm calling S. This is sigma 1s. So what we find out is that the principal stress that we calculate, sigma 1, is actually larger than sigma 1s. It's a matter of comparing the 176 to the 164. So this result says that the material has failed if you believe the maximum shear stress. Okay. So now we will do the same thing with maximum distortional energy. The boundary, the red ellipse, is given by sigma 1 squared minus sigma 1, sigma 2 plus sigma 2 squared is equal to sigma y squared. So if we find the intersection of the load line with the red line, I'm going to substitute in sigma 2 is equal to the minus 0.517 sigma 1. So this becomes sigma 1 squared minus a minus 0.517 sigma 1 times sigma 1 plus 0.517 sigma 1 squared is equal to sigma y squared. Combining those terms there on the left hand side gives 1 plus 0.517 plus 0.517 squared, sigma 1 squared is equal to sigma y squared. So therefore I solve for sigma 1, and that's equal to sigma y divided by, I guess I didn't actually write that number down, so I'll write down the whole expression here again. 1 plus 0.517 plus 0.517 squared, and there's a square root in front of that, of course. Sigma y, we said, was equal to 250. So sigma 1, the boundary there with the maximum distortional energy ellipse, occurs at sigma 1 equal to 187.2 megapascals. Again, I will call this a name subscripted D to say that that's where the load line has crossed this point here. So what we see here from this result is that the principal stress sigma 1 is less than sigma 1d. So we conclude that it didn't fail according to the maximum distortional energy approach. Just a quick run back on what we have done. We calculate the principal stresses sigma 1 and sigma 2. We need the numbers, and we need to know what quadrant that it's in, fourth quadrant in this case. We figure out what the load line is. Where does that load line intersect each boundary? The hexagonal one for maximum shear stress, found out that it fell outside of there. We found out where the load line intersected the maximum distortional energy ellipse, the red ellipse there in the figure. We found out in that case that the state of stress fell within. It was within the safe zone. Calculate principal stresses, find out if they fall inside or outside of the boundaries.